If I had to rate the difficulty of this question, I would say that it is a 2 out of 3. It's not that difficult, but it requires you to go ahead of the basics. Let's take a look. The first question, explain the term free fall. Like we've said before, the definition you're supposed to give is the definition on the exam guidelines. It says that free fall is the motion of an object under the influence of only gravity. The motion of an object under the influence of gravitational force, and only gravitational force, nothing else. If that is the case, then an object is in free fall. The second question, calculate the time it takes for ball A to return to its starting point. Let's take a look and see what is happening. So we have a ball A that is thrown vertically upward at a height h with a speed of 15 meters per second. At the same instant, a second identical ball B is dropped from the same height as ball A, as shown in the diagram below. Both balls undergo free fall and eventually hit the ground. Let's take a look at our question once more. Calculate the time it takes for ball A to return to its starting position. So this is where ball A is projected. It goes up to maximum height and starts going down, right? And then on its way down, it is obviously going to pass its starting position. So we want the time taken by the ball to go from its initial position, maximum height, and back to its starting position. Like I've said before, the time taken to go from the starting position to maximum height is the same time taken to go from maximum height to starting position on the way down. So we can basically calculate the time taken to reach maximum height and multiply that by 2 to get the entire time for the motion, starting position, maximum height, and back down to the starting position. That is one way of doing it. There's 2 ways of actually answering this question. I will show you both. So the first way, I'm taking the motion from the starting position to the maximum height. At the maximum height, we know that V will be equals to 0. Vi is equals to 15 meters per second. We have our acceleration being equals to 9.8, and we are interested in the time. With these 4 variables, the equation we need to use is Vf is equals to Vi plus A delta t, of which Vf is 0. Vi is positive 15 if we take up as positive, plus the acceleration minus 9.8 multiplied by delta t. So we have minus 15 being equals to minus 9.8 delta t. We just need to divide both sides by minus 9.8. We're going to have 1.53 seconds being equals to the change in time. But that is not the time we're interested in. 1.53 is the time taken to go from starting position to maximum height. We need to multiply that by 2 to get the entire time for the motion. So our time is 1.53 multiplied by 2, which is equals to 3.06 seconds. There we go. Time taken for ball A to return to its starting position. That is one way of doing it. Let me show you the other way. The other approach involves realizing that if our ball is projected with a velocity of 15 meters per second, when it passes the same point on its way down, it is going to have a velocity of minus 15 meters per second. This is always true. So considering the entire motion, using the same equation, Vf is equals to Vi plus A delta t, Vf would be minus 15 if we consider the entire motion. Vf is equals to 0 if we consider the motion from the starting position to the maximum height. If we consider the entire motion, Vf is minus 15. So we are going to have minus 15 being equals to 15 plus minus 9.8 multiplied by delta t. If we take 15 to the left hand side, we're going to get minus 30 being equals to minus 9.8 delta t. If we divide both sides by minus 9.8, we're going to get 3.06 seconds being equals to the change in time. So that is another way you can use to answer the second question. The third question, calculate the distance between ball A and ball B when ball A is at its maximum height. How much time is taken by ball A to reach its maximum height? We know fully well that it takes 1.53 seconds. So there we go. We have our time. Like I've said previously, when a question is talking about distance, you have to be thinking of displacement. How can you calculate displacement? In 1.53 seconds, ball A reaches its maximum height. So let's take a look. We have ball A going upwards to reach its maximum height. And then ball B is dropped. So it is going downwards. And we're interested in the displacement of A and B in 1.53 seconds. Let's start with the displacement of ball A. The displacement of ball A will be equals to VI delta t plus a half acceleration delta t squared. So what is the initial velocity of ball A? That is 15 meters per second. With the positive sign, if we take it up as positive, delta t 1.53 plus 1 divided by 2, the acceleration is minus 9.8. Delta t, it's 1.53. And we square that. This is equals to 11.48 meters upwards, right? As we can clearly see. And then on the other hand, the displacement of ball B, using the same equation, the initial velocity, it is being dropped, so that is 0. Delta t is 1.53 plus a half. The acceleration is minus 9.8. The time 1.53 squared. This is equals to minus 11.47 meters downwards, right? The negative sign is just showing us that it is moving downwards. So for ball A, we have a displacement of 11.48 meters upwards. And then for ball B, we have a displacement of 11.47 meters downwards. What we want is the distance between the two. So the distance will be equals to 11.48 plus 11.47. Distance is a scalar. You don't have to worry about the minus signs. You just add everything with a positive sign. This will give us 22.95 meters. They're 22.95 meters apart from each other. Calculate the speed with which ball A hits the surface of the water. Let's take a look at what's happening. A man throws ball A downwards with a speed of 2 meters per second from the edge of a window 45 meters above a dam of water. 1 second later, he throws a second ball B downwards and observes that both balls strike the surface of water in the dam at the same time. Ignore air friction. So we have a ball A that is being thrown downwards with an initial velocity of 2 meters per second. And 1 second later, we have a ball B that is also thrown vertically downwards. But they strike the ground at the same time, even though ball B is thrown 1 second later. The question is saying, let's calculate the speed with which ball A hits the surface of the water. Let's go ahead and see what information we have. We have the initial velocity of ball A. It is 2 meters per second downwards. It is thrown from the edge of a window 45 meters above a dam of water. So we have a height which will lead to a displacement of 45 meters. Obviously, we have the acceleration. The acceleration is 9.8. We're interested at the speed at which ball A hits the surface of the water. So we want to find VF. With these four variables, we can say that VF squared is equals to VI squared plus 2A delta Y. We're interested on VF. VI, 2 meters per second downwards. If we take up as positive, VI should be minus 2 squared plus 2 multiplied by the acceleration. The acceleration is always downwards, so that is minus 9.8. When a body is in free fall, the acceleration is always 9.8 meters per second squared downwards. And then delta Y is minus 45, right? When it strikes the ground, it is minus 45 meters from the starting point. So we're going to have VF squared being equals to 886. We're going to have VF being equals to 29.77 meters per second. The question says we should calculate the speed, so we don't have to give the direction. If we had to give the direction, it would be downwards because it strikes the ground on its way downwards. That is the first question. Let's take a look at the question that follows. So question 2, calculate the time it takes ball B to hit the surface of the water. Calculate the time it takes for ball B to hit the surface of the water. Okay, 3 marks. So we're not really supposed to be doing a lot of work. Well, we have a problem. With regards to ball B, we know that delta Y is equals to 45 meters downwards because it is projected from the same height. What else do we know? We know the acceleration, obviously, but we have 2 variables. We need a third variable in order for us to be able to find the time taken for ball B to hit the surface of the water. So you cannot use ball B to find the time taken by ball B to hit the surface of the water. You actually have to use ball A by realizing that ball B is thrown 1 second later, but they strike the ground at the same time. Let me show you how we can use ball A. Using ball A, we have the initial velocity, which is 2 meters per second. Okay, we just calculated the VF above. We know what the acceleration is. We can go ahead and find the time for ball A. So to find the time for ball A, we're going to have VF being equals to VI plus A delta T. Ball A strikes the ground with a velocity of minus 29.77, and then it was thrown with an initial velocity of minus 2 plus the acceleration minus 9.8 multiplied by the time. If we take minus 2 to the left hand side, we're going to get minus 27.77 is equals to minus 9.8 multiplied by delta T. So now it's just a matter of dividing both sides by 9.8. If we divide both sides by minus 9.8, we're going to get 2.83 seconds being equals to delta T. It takes ball B 2.83 seconds to hit the surface of the water, and ball A and ball B strike the ground at the same time. The only difference is that ball B is thrown 1 second later. So how much time is taken by ball B? The time will be equals to 2.83 minus 1. It was thrown 1 second later, which will be 1.83 seconds. That is another sneaky situation you have to be aware of. Let's move to the following question. Question 3, calculate the initial velocity of ball B. Okay, so let's take a look at the information we have with regards to ball B. We now know that the time taken by ball B is 1.83 seconds. We know the acceleration, 9.8. We know the displacement, 35, not 35, but 45 meters downwards. And we are looking for the initial velocity. With these four variables, we can say that delta y is equals to vi delta t plus a half acceleration delta t squared. So delta y, that will be minus 45 meters downwards. Vi is what we're interested in. The time is 1.83 plus 1 divided by 2. Acceleration is minus 9.8 and the time is 1.83 squared. So we're going to have minus 45 being equals to 1.83 vi minus 16.4096. Right, so taking minus 16.4096 to the left hand side, we are going to have minus 28.5904 being equals to 1.83 vi. If we divide both sides by 1.83, we're going to have vi being equals to minus 15.62, which is just equals to 15.62 meters per second downwards. That's all the negative sign implies. It implies that the initial velocity is downwards. So there we go. Question 3. Let's go ahead and take a look at question 4. So on the same set of axes, sketch a velocity versus time graph for the motion of balls A and B. Clearly indicate the following on your graph: initial velocities of both balls A and B, the time of release of ball B, and the time taken by both balls to hit the surface of the water. Right, let's go ahead and have our set of axes. This is our time in seconds, and this is our velocity in meters per second. Because ball A strikes the ground in 2.83 seconds, on the time axis, we can have 1, 2, 3. The initial velocity for ball A is minus 2 meters per second. That is at t is equals to 0. So we have a coordinate right there. And for ball B, the initial velocity is 15.62 meters per second downwards. So let's go ahead and have minus 15.62. It is at t is equals to 1. So this is the first point for ball B. And then ball A strikes the ground at 29.77 meters per second downwards. So minus 29.77. That is at t is equals to 2.83. So somewhere here, it's where ball A strikes the ground. Now we just have to go ahead and join the dots. So for ball A, we're going to have something like that. And then for ball B, we're going to have something very similar. They strike the ground at the same time. So the two graphs should end at the same place. So somewhere here, it's where the two graphs should end. So right, this is our velocity time graph. Let's see if we indicated all that we need to do. Initial velocity for both balls A and B. Initial velocity for ball A. Initial velocity for ball B, which is 15.62. The time of release of ball B, that is at t is equals to 1. So we are able to indicate that. The time taken by both balls to hit the surface of the water, t is equals to 2.83, somewhere here. We've indicated that. So there we go. We have all that we need. The marker location is 5 marks. As you can see, we have 1, 2, 3, 4 ticks. The fifth tick is probably coming from ensuring that these two lines are actually parallel to each other. Why do we need the two lines to be parallel to each other? Because the gradient is 9.8 on both lines, the acceleration. This is A and this is B. We need to indicate that. A ball is dropped from the top of a building 20 meters high. Ignore the effects of air resistance. There isn't a lot going on in this question. The first question, define the term free fall. So free fall is the motion. Keyword, motion. Free fall is the motion of an object under the influence of only gravity. The motion of an object under the influence of only gravity. Question 2. Calculate the speed at which the ball hits the ground. So again, our ball is just being dropped from a height of 20 meters. There isn't a lot going on. So we know that VI is equals to 0 meters per second. If it is being dropped, the initial velocity will be 0. We always have the acceleration, 9.8 meters per second squared downwards. We have VI, we have the acceleration, we need one more variable, we need one more data point in order for us to answer this question. We're interested on the speed at which the ball strikes the ground. It is dropped from a height of 20 meters. So we have our displacement as it strikes the ground. Our displacement is 20 meters downwards, of which when we substitute, when we are taking up as positive, we'll put a minus sign. Now what we want is VF, the velocity at which the ball hits the ground. We're going to have VF squared being equals to VI squared plus 2A delta Y. So VF squared will be equals to 0 squared. Well, you might be asking yourself, why are we saying 0 squared? I mean, we know that 0 squared is 0. So is it necessary? Do we really have to do that? Yes, it is necessary. Even though we know that 0 squared is 0, we need to show that, right? There's a mark for substituting. If you don't show that 0 squared is 0, you're not going to get that mark. Plus 2A. A is the acceleration, minus 9.8, right? 9.8 meters per second squared downwards. And then delta Y, the displacement, it is also downwards. So we're going to have minus 20. So VF squared is equals to just 2 multiplied by minus 9.8 multiplied by minus 20. I'm getting 392. So what we need to do at this point is to take square roots on both sides. So VF is equals to 19.7989. If we round that off to 2 decimal places, we're going to have 19.8 meters per second downwards. Well, we don't have to indicate the direction. The question says the speed, so we are only interested on the magnitude and not the direction. But anyway, stories. That is question 2. Let's move to the third question. So the third question, calculate the time it takes the ball to reach the ground. Calculate the time it takes the ball to reach the ground. Let's see how we can do that. We have our initial velocity, obviously, which is equals to 0 meters per second. We have our acceleration, which is 9.8. We have our displacement, which is minus 20, right? And then we have our, what else do we have? Well, we're looking for the time, delta T. We're interested on the time. With these 4 equations, with these 4 variables, we can use delta Y is equals to VI delta T plus F acceleration delta T squared, of which delta Y is minus 20. VI is 0, so we're going to have 0 multiplied by the change in time, right? Plus F, the acceleration is minus 9.8. Delta T is what we are interested in. Obviously, you can also use the equation VF is equals to VI plus A delta T, because we calculated VF above, but I don't want to use that equation. Let me tell you why I'm running away from that equation. Let's say my answer was VF is equals to 30 meters per second. This is wrong. We know that VF is supposed to be 19.8. But let's say I made a mistake and my VF was 30 meters per second. This will imply that my answer to question 3 will also be wrong because I'm using a wrong value. So all the time, if I can answer a question without using a value that I calculated myself, I will always choose that approach, right? I always try not use a value that I calculated myself. If I can, most of the time you can't, but in a position like this, I can, so I'm not going to use a value that I calculated myself. I'm going to use the values that I'm extracting from the question itself. It is really helpful. So minus 20, 0 multiplied by the change in time, that's 0. And then a half multiplied by minus 9.8, that is minus 4.9 delta t squared. So what are we doing? We're dividing both sides by minus 4.9. We're going to have delta t squared being equals to 4.0816. So let me go ahead and take square roots on both sides. I'm going to have delta t being equals to 2.02 seconds. There we go. We have the time taken by the ball to reach the ground. Question 4. In question 4, we're supposed to sketch a velocity time graph for the motion of the ball. No values are required, right? It doesn't get easier than this. We're not even supposed to indicate any values. So there we go, our y-axis and our x-axis. And then on the y-axis, we have the velocity in meters per second. On the x-axis, we have the time in seconds. The initial velocity of our ball when t is equals to 0 is 0. And then our ball starts going down, right? So its velocity will be negative right after. That is because we are taking up as positive. We're supposed to have something like that, and that is all we need to do for this question. No values are required whatsoever. The velocity time graph we are asked to sketch in this problem is a thing of beauty. Stick around so I can show you what I'm talking about. The first question, why is the ball considered to be in free fall during its motion? Let's go through the question statement and figure out what's going on. So we have a ball that is projected vertically upwards with a speed of 10 meters per second from point A. The ball hits the ground after 3 seconds. It is in contact with the ground for 0.2 seconds and then bounces vertically upwards, reaching a maximum height of 8 meters at point B. See the diagram below. We can clearly see this is point A where it is projected, and this is the maximum height B it reaches after its first bounce. So the first question, why is the ball considered to be in free fall during its motion? That is because the only force acting on the ball is gravity. When the only force acting on the ball is gravity, we deem it to be in free fall. We deem it to be a projectile. It has been given an initial velocity and now it's moving under the influence of only gravity. That is the answer to the first question. The second question, calculate the height of the building. We want to calculate the entire height of this building. How can we possibly do that? Let's take a look at the information we have. We have the velocity at which the ball is projected at, our VI, which happens to be 10 meters per second. Obviously, we always have the acceleration. It is 9.8 meters per second squared downwards. That is when our object is in free fall. Another piece of information is the time taken to hit the ground. Delta t is equals to 3 seconds. And then what we want is delta y, the height of the building. The height of the building will be delta y because the displacement of the ball will give you the height of the building. We don't care about the fact that the ball goes up first. That will not affect our displacement. Our displacement will be the height of the building. That is the only thing we are interested in. Okay, so with these four variables, obviously we can say that delta y is equals to vi delta t plus a half acceleration delta t squared. Let's go ahead and substitute. We take up as positive, so vi will be 10, delta t is 3 seconds, plus a half. The acceleration is minus 9.8 multiplied by 3, and we square that. So let's take a look. 10 multiplied by 3 plus a half multiplied by minus 9.8 multiplied by 3 squared. That is equals to minus 14.1. So our height is equals to 14.1 meters. That is the height of our building. Right, let's take a look at the question that follows. Calculate the speed with which the ball hits the ground. Calculate the speed with which the ball hits the ground. So let's take a look at the information we have. We have the initial velocity, which is still 10 meters per second. We have the acceleration 9.8 if it's free falling. What else do we have? We have delta t. Delta t is equals to 3 seconds, and we want to find the velocity at which it hits the ground, which we can take as vf. Okay, with these four variables, pretty much straightforward, right? Doesn't get easier than this. We are gonna have vf being equals to vi plus a delta t. Vf is what we're interested in. Vi is 10, the acceleration is minus 9.8, and the time is 3 seconds. So let me just go ahead and put that in my calculator. Let me see what I get. I have minus 19.4. So VF is minus 19.4, which is just 19.4 meters per second. We don't have to indicate the direction because the question is asking for the speed and not the velocity. Well, there we go. Let's move to the question that follows. Question 4. So question 4, calculate the speed with which the ball leaves the ground. Okay, so we know that our ball will strike the ground, right? And then after some time, 0.2 seconds to be specific, it is going to leave the ground and then go up until it reaches point B, its maximum height. So when it reaches its maximum height, we know that we're going to have a VF, which is equals to 0. The velocity at the maximum height is 0. We're interested in VI, the initial velocity, the velocity as it leaves the ground. Okay, we cannot use 10 meters per second anymore. No. We're interested on the velocity as it leaves the ground. Right. So the acceleration still 9.8, and we are given delta y, the displacement from the ground to point B is 8 meters. So with these four variables, which equation can we use to find VI? VF squared is equals to VI squared plus 2a delta y. That should be quite easy to see. VF is 0, so we have 0 squared being equals to VI, what you're interested in, plus 2. Acceleration is minus 9.8, delta y is 8. Okay, so if we take VI squared to the left hand side, we're gonna have minus VI squared. So minus VI squared is equals to minus 156.8. Dividing both sides by minus 1, VI squared is equals to 156.8. Let's take square roots on both sides. We're going to have VI being equals to 12.52 meters per second upwards, right? That is the velocity as it leaves the ground. Well, the question says speed, so let's not indicate the direction because the question says speed. There we go. That is question 4. Let's move to the last question. Question 5. The question we're interested in, the velocity time graph. Let's go ahead and take a look. So the velocity time graph. The question is saying, draw a velocity time graph for the complete motion of the ball from A to B. Show the following on the graph. The magnitude of the velocity with which it hits the ground, the magnitude of the velocity with which it leaves the ground, and the time taken to reach the ground, as well as the time at which it leaves the ground. Okay, right, let's go ahead and see how we can possibly do that. We need our set of axes, obviously. So there we go. We have our y-axis and we have our x-axis. In our y-axis, we have the velocity, obviously, in meters per second. And on the x-axis, we have the time in seconds. So this is velocity in meters per second. So let's go ahead and fill out the x-axis. It hits the ground after 3 seconds. So let's say 1, 2, 3, 4, 5, 6. Okay, and then its initial velocity, we're taking up is positive. Its initial velocity is 10 meters per second. That is its initial velocity. Okay, so it starts here, and then gravity is acting against our motion, right? Our object is going up, gravity is going down. So the velocity decreases until it reaches its maximum height. Well, we don't have the time taken to reach maximum height, but we have the time taken to hit the ground. But what is the magnitude of the velocity as it hits the ground? We calculated that above, so let's go ahead and find out. The velocity is 19.4 meters per second. And then as it leaves the ground is 12.52. Okay, so let's go ahead and have that. As it hits the ground, the velocity is minus 19.4. Okay, so if 10 is somewhere here, then minus 19 should be somewhere here, right? So in 3 seconds, this is what we have. Our object is striking the ground. So let me just go ahead and join those 2 dots for the sake of clarity. It is in contact with the ground for 0.2 seconds. It then leaves the ground with a positive velocity because it is going up with a velocity of 12.52. Let's say this is 12. So somewhere here is where it leaves the ground with a velocity of 12.52 meters per second upwards. So we need another data point somewhere here, and then it is gonna go up until it reaches maximum height. Okay, we don't have the amount of time taken to reach maximum height, but that doesn't matter. Okay, there's no mark for that if we didn't calculate it. So yes, we're gonna have something like this, but as you can see, there's a gap here. What do we do in a situation like this? We have to join the 2 lines with a dotted line. We have to join the 2 lines with a dotted line. So something like this. Right, there we go. This is our velocity time graph. So let's see if we included all that we needed to include. The magnitude of the velocity with each it hits the ground. Here we go. Minus 19 point something. Okay, and then the magnitude of the velocity with which it leaves the ground, we have indicated it 12.52. And then the time taken to reach the ground, 3 seconds, we have indicated that. And then as well as the time at which it leaves the ground. We're supposed to indicate the time at which it leaves the ground. This is another special problem. Let's go ahead and take a look. The first question, we are supposed to calculate the time taken for stone A to reach its maximum height. But before we can do any of that, let's go through the question statement so I can show you what is special about this problem. We have a stone A, which is projected vertically upwards with a speed of 12 meters per second from a height h above the ground. At the same instant that stone A is projected upwards, stone B is thrown vertically downwards from the same height, right, at an unknown speed v downwards, as you can clearly see from the sketch. So that is the information we have. The question: calculate the time taken for stone A to reach its maximum height. So with regards to stone A, we know that it is projected vertically upwards with an initial velocity of 12 meters per second. We know the acceleration, like we always do in free fall, that is 9.8 meters per second squared. Apart from the acceleration, we have VF, because we are interested on the time taken to reach maximum height. We know that the velocity at the maximum height is 0. We are interested on the time, delta t. With these 4 variables, we can use VF is equals to VI plus a delta t. VF is 0 because we are interested in the maximum height. VI is 12 meters per second with the positive sign because we are taking up as positive, plus the acceleration minus 9.8. That is because the gravitational acceleration is downwards and we are taking up as positive. Delta t is what we are interested in. We are obviously going to take 12 to the left hand side. We're going to have minus 12 being equals to minus 9.8 delta t. It should be quite easy to see what we need to do at this point. We have to divide both sides by 9.8, minus 9.8, okay? So we're going to have delta t being equals to minus 12 divided by minus 9.8. If you put that in your calculator, you're going to get 1.22 seconds. So it takes 1.22 seconds for stone A to reach its maximum height. That is quite basic. There's nothing special we're doing there. But take a look at the question that follows. Question 2. So question 2, it says that when stone A reaches its maximum height, the speed of stone B is 3v. They are projected at the same time, right? When stone A is being projected upwards, stone B is being projected downwards with an initial velocity of v. But when stone A reaches its maximum height in 1.22 seconds, the speed of stone B is 3v. The question is saying calculate the speed v with which the stone B is thrown downwards. As you can see, this is not a usual style of questioning we come across. We have to deal with variables, right? Vi, the initial velocity of our stone B, is v, and then Vf is 3v, right? At the instant stone A reaches its maximum height, when delta t is equals to 1.22 seconds, the final velocity of stone B is 3 volts. So we have Vi, which is v, we have Vf, which is 3v, we have delta t, which is 1.22 seconds, and we also have the acceleration, 9.8 meters per second squared downwards. We want to find the variable v. How can we do that with these 4 variables? Again, Vf is equals to Vi plus a multiplied by delta t. I'm being guided by the variables, okay? So the most important thing in questions like this is to not panic. As soon as people see variable, they usually just conclude that, no, I've not solved a problem like this before, we didn't cover this in class, it's so unfair, I'm just gonna skip it. But no, this is a very basic question. There's just one twist to it that you need to realize. As soon as you break down this question, it will be relatively easy. It's not that difficult, right? You just need to take your time, go through the basics, pick the formula, and solve your problem. Let's carry on. Vf will be minus 3v. That is because we are taking up as positive, right? And then Vi will be minus v. Yeah, because it is a variable, it doesn't mean that now we have to throw all the physics out of the window. No, 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 no. We still have to respect the physics. We still need to respect scalars, treat them as such, treat vectors the way they need to be treated, putting into consideration the direction, so on and so on. Plus the acceleration, which is minus 9.8. The time is 1.22. So we're going to take minus v to the left-hand side is going to be plus v. So we're going to have minus 2v being equals to, what is minus 9.8 multiplied by 1.22? That is minus 11.956. Clearly, we need to divide both sides by minus 2. And when I do that, I get 5.98 meters per second. This is the speed v with which stone B is thrown downwards. Okay, not difficult at all. You just need to identify your initial velocity, your final velocity, and maybe the time was also a bit tricky because the speed of stone B is 3v when stone A is at its maximum height, and we know fully well that stone A is at its maximum height in 1.22 seconds. So I guess it was also a bit tricky to identify that the time is supposed to be 1.22, but apart from that, we're just sticking to the basics. Okay, the question that follows, question 3. At the instant stone A passes its initial position on its way down, stone B hits the ground. Calculate the height h. We're supposed to calculate the height h. Right, so let's see. We can use stone A or we can use stone B. I think both can work, but let's try using stone B. If we're using stone B, our VI is going to be equals to 5.98 meters per second downwards, right? It's what we just calculated above, the value of V. And then the acceleration, 9.8, obviously. And then it's supposed to calculate the height h. The displacement of stone B as it strikes the ground will be the height h, right? So delta y, it's what we are interested in. Which other variable do we have? We actually have the time. Let me show you how. Let's take a look at the question again. At the instant stone A passes its initial position on its way down, stone B hits the ground. Calculate the height h. We've talked about this previously, right? If it takes 1.22 seconds to go from initial position to the maximum height, this is 1.22 seconds. It will take 1.22 seconds to go from the maximum position to the initial height once more. It will also take 1.22 seconds. So the time taken for the entire motion is 1.22 multiplied by 2. And we know fully well that that is the time taken by stone B to strike the ground. As stone A passes its initial position on its way down, stone B strikes the ground. Okay, so we have the time, but it is not easy to see. You have to think about it a bit. But we have covered this in our previous problems, so it should not be an issue whatsoever. You should be able to answer this question using just the knowledge we have covered. Right. So let's see, if we have delta t, vi acceleration, delta y, we can obviously say that delta y is equals to vi delta t plus a half acceleration delta t squared. So vi, that is minus 5.98. I'm always taking up as positive unless stated otherwise. And then the time is 1.22 multiplied by 2, which will be 2.44. So we have 2.44. Always positive is a scalar. Plus a half. The acceleration is minus 9.8. The time is 2.44. And we square that. This is equals to minus 43.7 0.7638. So h will be equals to 43.76 meters. That is the height h, which we are supposed to calculate. Question 3. Let's move to question 4. Velocity time graph. Let's go ahead and take a look. So sketch velocity time graphs for the complete motions of stone A and B on the same set of axes. Label your graphs for stones A and B clearly. Show the following on the graphs. The time taken for stone A to reach its maximum height, 1.22 seconds, and the velocity with which stone B is thrown downwards. Let's say 0.5, 1, 1.5, 2, 2.5. Okay, let's use that time interval. Okay, I'm deciding to use this time interval because the entire motion of both balls takes 2.44 seconds. So we're supposed to indicate the time taken for stone A to reach its maximum height. It takes 1.22 seconds. We know that for sure. But its initial velocity is 12 meters per second. So let's see, 12 meters per second is somewhere here. So this is its initial position, its initial velocity when t is equals to 0. And then in 1.22 seconds, its velocity is equals to 0, right? Because it reaches its maximum height. It starts going down until it passes its initial position when t is equals to 2.44. Okay, we know that for sure. And then its velocity should be minus 12 when it passes its initial position. So let's go ahead and join those dots. There we go. This is the graph for stone A. Let's go ahead and have the velocity time graph for stone B. Its initial velocity is minus 5.98. Let me verify. Okay, yes, minus 5.98. So if this is minus 6, then somewhere here, minus 5.98. In 2.44 seconds, its velocity is 3v, right? We should be very close to minus 18. So let me just draw that line. This is where our stone B ends up. So there we go. We have the velocity time graphs for the two stones, A and B. Determine the time that the ball is in contact with the floor before the first bounce. That is the second question. This is a very special problem, okay? We are given a position time graph, as you can clearly see on the left hand side, and we're supposed to answer questions based on that position versus time graph. So let's go ahead and take a look and see what's happening. A small ball is dropped from a height of 2 meters and bounces a few times after landing on a cement floor. Okay, we can see clearly from the position time graph that it is indeed dropped from a height of 2 meters. Okay, it is dropped, so that gives us the velocity. We now know that the initial velocity at 2 meters above the ground is 0 meters per second. Okay, let's carry on. Ignore air friction. If we're ignoring air friction, then as soon as it is dropped, it is in free fall. It is a projectile. The only force acting is gravitational force. The position time graph below, not drawn to scale, represents the motion of the ball. Right, that's all we have. Let's go through the question once more. Determine the time that the ball is in contact with the floor before the first bounce. Okay, so our ball is being dropped from this point and it starts going down. Okay, it strikes the ground at this point when t is equals to 0.64, and then it leaves the ground at t is equals to 0.67. So between 0.67 and 0.64, our object is in contact with the ground. So how much time does the object spend in contact with the ground? We're going to have t being equals to 0.67 minus 0.64. Okay, so what is 0.67 minus 0.64? We have 0.03. So t is equals to 0.03 seconds. The ball spends 0.03 seconds in contact with the ground. That is the answer to the second question. Okay, the third question, on the other hand, determine the time it takes the ball to reach its maximum height after the first bounce. What we are interested in is the time taken by the ball to reach its maximum height after the first bounce. So this is what we are interested in. How much time does it take after leaving the ground to reach the maximum height? That's what you are interested in. Okay, there's a couple of ways we can answer this question. We can use equations of motions, or we can use the fact that if it takes 1 second to go from the ground to maximum height, it will also take 1 second to go from maximum height and strike the ground. So what I'm proposing here is that this is 1.9 and this is 0.67. We can say t is equals to 1.9 minus 0.67. So let me just go ahead and put that in my calculator. I'm getting 1.23 seconds. So this is the time taken to leave the ground, go to maximum height, and strike the ground again. So what we're proposing is that the time taken to reach maximum height will be equals to, from here to here, it's 1.23. So going from here until maximum height will be half of that. And then maximum height back to striking the ground will be half of that, because the acceleration is the same. So delta t will be equals to 1.23 divided by 2. So what is 1.23 divided by 2? I'm getting 0.62 seconds. So if we use that fact, we know fully well that this is correct, right? We're not making an assumption. We know fully well that it is correct. We have seen it time after time that it is correct. Also, if you think about it from an acceleration point of view, you should also see that it holds. So that is one way of doing it. We end up with an answer of 0.62 seconds. Let's do the question that follows. So question 4, we are supposed to calculate the speed at which the ball leaves the floor at the first bounce. So this is where the ball leaves the floor at the first bounce. Okay, if we only consider this part of the motion, you will realize that VI is what we are interested in. VF is equals to 0 at the maximum height. Delta Y is the displacement, which is 1.85 meters. As you can clearly see right here. So there we go. We have delta Y, 1.85 meters. The acceleration obviously is 9.8 meters per second squared downwards. With these 4 variables, we can say that VF squared is equals to VI squared plus 2A delta Y. VF is 0, so we have 0 squared being equals to VI. So that is VI squared plus 2. The acceleration is minus 9.8. We take it up as positive, and the displacement is plus 1.85. So 0 squared, that is 0 obviously. So we're going to have 0 being equals to VI squared. What is 2 multiplied by minus 9.8 multiplied by 1.85? That is minus 36.26. So we have 36.26 being equals to VI squared. What we need to do here is to take square roots on both sides. If I do that, I am getting 6.02 meters per second being equals to VI. The question says the speed, so we don't have to indicate the direction. That is all that we need to indicate. So there we go. That is question 4. Let's go ahead and do question 5. In question 5, we're supposed to calculate the time t indicated on the graph for 6 marks. So let's just get rid of all this for the sake of clarity. We're interested on the time t, and that is for 6 marks. Let's make sense of that. This is the part of the motion that I'm considering. If you pay attention to that part of the motion, you should realize fairly quick that Vi is equals to 0, because this is maximum height. So the initial velocity there should be 0 meters per second. Okay, so we have the initial velocity. We also have the acceleration, like we always do in free fall, 9.8. So Vi, acceleration, what else do we have? We have the displacement. When we strike the ground, the displacement will be 1.2 meters downwards. You can clearly see here that the position is 1.2 meters above the ground. So Vi, acceleration, delta y, let's find delta t. Okay, but there's a twist to this delta t that we are looking for. But let's figure it out first, and then I'm going to show you what I'm talking about. So with these variables, which equation can we use? Okay, I think delta y is equals to Vi delta t plus I have acceleration delta t squared should hold up really well. So there we go. We have delta y 1.2 meters downwards, because we're starting from maximum height until we strike the ground. So we're gonna have minus 1.2. Vi is 0, maximum height. Delta t is what we're interested in. Plus I have acceleration is minus 9.8. Delta t is what we're interested in, delta t squared. So minus 1.2 is equals to 0 multiplied by delta t, that is 0. So that falls away. I have multiplied by minus 9.8, that is minus 4.9 delta t squared. So what we need to do is to divide both sides by minus 4.9. So let me just go ahead and do that. I am getting 0.2449. I'm rounding off to 4 decimal places because I'm not at the final answer. This is equals to delta t squared. So let's go ahead and take square roots on both sides. When I do that, I get 0.49. 0.49 seconds is equals to delta t. Right, let's go ahead and make sense of this 0.49 seconds. Like I said, there's a twist to it. We're looking for t on the position time graph. These right here. We're not looking for delta t from maximum height until we strike the ground. Okay, so let's make sense of that delta t. We know for sure that from maximum height until we strike the ground is 0.49 seconds, right? But that also implies that from the ground until maximum height, we took 0.49 seconds. So from 1.97 to t is 0.49 plus 0.49. So t is equals to 1.97 plus 0.49 multiplied by 2. So what is 1.97 plus 0.49 multiplied by 2? I'm getting t being equals to 2.95 seconds. Okay, there's other ways you can play around with how you are getting to 2.95 seconds, but whatever way, if it makes sense, you should get 2.95 seconds. This is the answer, right? You can take a different approach. I'm quite sure there's quite a few ways you can get to t being equals to 2.95, but ultimately we should be getting t is equals to 2.95 seconds. Well, this was an interesting question. Until I see you next time. Is the object's acceleration at its maximum height upward, downward, or 0? When the only force acting on an object is gravity, the acceleration always is 9.8 meters per second squared downwards. We covered that at the very start of our series where we use the simulation. So the answer here is downward. When the only force acting on an object is gravity, the acceleration will always be downward, irregardless of the part of the motion. Whether we at the start, whether we at the maximum height, it doesn't matter. The acceleration is 9.8 meters per second squared downward. The only thing special about the maximum height is that the velocity is 0, but the acceleration doesn't change. It is still 9.8 meters per second squared downward. So that is the first question. The second question, calculate the magnitude of the velocity at which the object strikes the ground. Well, let's go through our question statement. An object is projected vertically upwards at 8 meters per second from the roof of the building, which is 60 meters high. It strikes the balcony below after 4 seconds. The object then bounces off the balcony and strikes the ground as illustrated. We are looking for the magnitude of the velocity as the balcony strikes the ground. We have the velocity at the top of our building when our object is projected, which we can use as our VI. So we have VI being equals to 8 meters per second. We have VF, which is what we're looking for. The acceleration is and always is 9.8. On the other hand, the change in time we're given is 4 seconds. The object strikes the balcony after 4 seconds. Which equation can we use with these 4 variables? Well, VF is equals to VI plus A delta T. Taking up is positive. If we substitute, we're going to have 8 plus the acceleration, which is minus 9.8 multiplied by delta T. It's a scalar, so it's always positive. Minus 31.2, which is just equals to 31.2 meters per second. The question says, let's calculate the magnitude. So we don't have to worry about the direction. We can just leave the answer as it is. If we were looking for the velocity, we would have to give the direction, which would be downward because our projectile strikes the balcony on its way down. But here we are only interested on the magnitude, so we can leave it like that. That is the second question. Let's move to the third question. In the third question, we are supposed to calculate the height h of the balcony above the ground. As soon as I hear height, I'm thinking displacement. Some way, somehow, I have to calculate the displacement. Because how can you calculate height without calculating displacement, right? So that is a tip right there. When the question talks about height, you are definitely going to calculate the displacement at some point of time. So we want the height of the balcony from the ground to the balcony. This is the height we are interested in. But let's take a look at the information we have. What we have is the initial velocity at the top of the building and the velocity as our object strikes the balcony. With that information, we can find the height from the top of the building to the balcony. If we say that the height from the top of the building to the balcony is k, then the height from the ground to the balcony will be 60 minus k, because from the ground to the top of the building is 60 meters like we are given. So we can just find the displacement from the top of the building to the balcony and use that to find the height. Let me go ahead and show you what I'm talking about. Our initial velocity is 8 meters per second. Our change in time is 4 seconds. Our acceleration is 9.8 meters per second squared. We are interested in the displacement. With these 4 variables, which equation can you use? Well, we can say that delta y is equals to vi delta t plus a half acceleration delta t squared. But because we have vf in the equation we just solved, you can also use vf squared is equals to vi squared plus 2a delta y. But let's carry on and just use this one. Vi, that is 8, we're taking up as positive. Change in time 4 plus a half. Acceleration is minus 9.8 4 squared. This is equals to minus 46.4 meters. So this right here is 46.4 meters. The displacement of our projectile is minus 46.4 because we are taking up as positive. So if it is going down, the displacement must be negative. But from the top of the building to the balcony, it will be 46.4 meters. Our height will therefore be equals to 60 minus 46.4, which is equals to 13.6 meters. So the balcony is 13.6 meters above the ground. Questions like this one will always be there in the exam. Questions where you have to analyze the situation in hand. A situation that you'll probably be coming across for the very first time. So don't be comfortable and just think that it's just a matter of writing down the variables and substituting.